All right, kids, we're back for part two. We're just going to complete the last example here. It's not actually very different than the other ones, but I think it was a good idea to take a break, let you digest what was going on, and we'll take this one for a spin. What you could do is you could even treat this as a pop quiz if you like and just try it yourself, or you can just watch me do it. Okay, so what we have is we have some tide height data for Banfield. So you may or may not know this, but the tides are pretty interesting. They actually go up and down like a sine wave, again, because it's dependent on the rotation of the Earth and where the moon and the sun is and all that sort of jazz. So let's find a sinusoidal function that predicts the tide height at any time. I have a fly buzzing around me so you can see me swat at it. There we go. Yeah, he wants to be part of the video. Everyone wants to be a celebrity. Okay, so anyway, let's find a sinusoidal function. So the first thing I'm going to do with any question like this is I'm going to just get a very rough sketch, because if I can't picture it, I can't do it. So I'm going to do a little sketch here, the height as a function of time. So we're talking about time here. In our last example, we were talking about days of the year, and we kind of enumerated it by calling January 1st the first day. I'm going to do something similar where I'm going to call 0. That's going to be equal to 12 o'clock a.m. or midnight. And if I want to then turn this guy here into a number, I can't use time because time is sort of messed up. It's not base 100 like all our other numbers. It's base 60. So 6 hours and 36 minutes. This is actually 6 hours and 36 minutes. We're actually going to want to do a little unit conversion here to turn this into just hours. So 1 hour is 60 minutes. So 36 divided by 60, we would get out our calculator, which I guess I've got to get my little virtual one going. It's nice for you to see the calculation here. So let's turn this guy on. Okay, so I'm going to go 36 divided by 60. And that is going to get me 0.6, which now in retrospect is something I probably could have done. Okay, so this becomes 6.6 hours. Okay, so that's important. So over here where we've got the time, maybe this we'll call noon, which is 12, which of course corresponds to 12 p.m. That's noon. This is midnight. Anyway, okay, so what we have here is we've got 6.6. So this is about 6.6 hours. So we're going to put a point there, and that's going to be at 0.41, so it's right there. Okay, and then we've got this other guy over here, which is 12:48. Now this one we're going to have to turn into 12 hours and 48 minutes, and you can't just write 12.48. So this one here, we're going to do something similar. I'm going to use my brain. 48 over 60, I believe, is reducible to 4 over 5, so that is going to be 0.8 hours, so that means we're at 12.8 hours. Okay, so 12.8 hours is going to be right about there. So that's going to be at the maximum height, which is 2.91 meters. All right, so right there. So there's my 2 points. Okay, my low is there, my high is there, and then I can see we're going to have a sinusoidal function that's going to look something like that. Let's try and make it look sort of more appropriate. There we go. Okay, and then something like so. Okay, so when we have this graph, this is going to be really helpful. At least it certainly will be for me. And let's just move the calculator down there for now. So when we have a picture of our graph, we can see it has a general shape. Now we want a sinusoidal function. Do we want cosine or sine? Turns out for a lot of these problems, it's going to be really handy to have cosine. And we can see that cosine starts here. You could make an argument that negative cosine starts down there, but I am always a fan of making things positive when we can. One thing I'm a little concerned about or thinking about is I wonder if this kind of goes back and has another starting point like there. So I'm just going to do a little thing. I'm going to figure out what is the horizontal distance between the trough and the peak. So it's 12.8 minus 6.6. So that is 6.2 hours. So that actually tells me something very interesting, very important. It means that there's a horizontal distance between here and here of 6.2 hours, and that's going to correspond with a time right there. And I can see that's going to be equal to 0.4 hours. So even though we're not told in our data there's going to be another high tide at 0.4 hours, which is however many minutes, we can figure that out, but I'm not going to worry about it. So coast starts here, but it also, coast also starts here. And this is probably the one I'm going to use, because even though 0.4 or 12.8 would both be correct phase shifts for my coast graph, we do tend to want to take the smaller one. So we'll be using that one. All right, so when we go to write that down, what we're going to do is we're going to say that C equals 0.4. Again, this is for positive cosine. Now A is the amplitude, so the amplitude will work out using the formula. I'm not going to write the formula, I'm just going to do the calculation. It's 2.91 minus 0.41 over 2. And if I'm correct here, that is going to be 2.5 over 2, so that's 1.25. Oh, that's a nice round number. B is equal to 2 pi over the period. Okay, so the period here, we can see that the period in total, to go from here all the way to here, so I don't want to overcrowd my picture too much, but I will write that the period goes from here to here. We can see the period is equal to 6.2 plus 6.2. So from peak to peak, it's equal to 12.4. Okay, so that's important. So now we can go 2 pi over 12.4. And that is going to be some value here. This is something that you could probably simplify if you wanted to really turn this into a fraction here. You could write it as 20 pi over 124, which is multiplying top and bottom by 10. And then you could probably divide top and bottom by 4, so that would be 5 pi over 31. And I think that should actually be it. Just a quick thing. Yes, okay. 124 divided by 4 is 31. Okay, so you don't necessarily have to leave it as an exact quantity, but I saw that it was possible to do so, so that's what I'm doing. Okay, D. So D, remember, is the average of the high and the low point, so it's going to be 2.91 minus, plus 0.41 over 2. We're always adding to do an average. So that is 3.32 over 2, which is going to be 1.66, I believe. Okay, once we've got all that, we can put it together, so therefore we can say that the height as a function of the time is equal to 1.25 cosine 0.4. Whoops, sorry, my mistake. B goes in here, so that's 5 pi over 31. That's a really funny looking 3, that upsets me. Okay, and then we've got T minus 0.4, and then we could also have this as plus 1.66. And that should be the equation. So the one thing we will just have to make sure we're saying here is T in hours, and we're starting with midnight equals 0. Okay, so it's really important just to specify that. Okay, so now we're going to say use that function to estimate the tidal height at 3 p.m. So we're going to say what is the height at 3? Now this is a little sneaky thing. It's 3 p.m. So in the 24-hour clock, this is 15 hours. So that will be what is my height at 15 hours, because we're going 15 hours from midnight. So 1.25 cos, and then the rest is just putting in the quantities. Okay, so we grab our calculator, and this part's not extremely hard. What mode do we have to be in? You got it, radian mode. So we're going to make sure we're in radian mode here. So we're going to go 1.25. We're going to multiply that by cosine. Now we got to be careful with the brackets. So we've got 5 pi over 31. And then we're going to start another bracket for 15 minus 0.4. Close that up, and then close again for the square bracket, and then we're going to add 1.66. So that gives me 2.21. All right, so we go over here and we say 2.21 meters. Does that sound like a reasonable answer? We know that the tide oscillates between a low of 0.41 and a high of 0.291. We're closer to being on the higher side of things, which means we're probably a little closer to the high tide. So the high tide happens at 12:48 p.m. 3 p.m. is a couple hours later, so it seems like a reasonable answer. Now, in case you're wondering, are tides really sinusoidal? Some people have never seen this, so I just think it's an interesting thing. Let's just take a jump over here. One thing I look up quite often is the White Rock tide tables, because I live right by the beach and I like to know. So if you're kind of curious, are the graphs for the tides actually sinusoidal? You can see that they sort of are. So if you actually look at this here, this gives us our sinusoidal graph for the tides. Now you might notice this is not a pure sinusoidal function. It's got a couple extra humps, and you see the humps themselves are kind of changing. If you actually look at this here, maybe I'll just quickly grab a screenshot because I think this is really worth thinking about. If you actually go down, let's say here, and you look at this, you can see that you've actually got a combination of some sine waves going if you look hard enough. So here you can see the successive low tides of every day actually make a part of a sine curve here, and you can see the high tides actually make part of a sine curve as well. Within those low and high tides, you've got some sinusoidal action going here where it goes up and down and up and down and up and down. What you actually have is you actually have the combination of two different sine curves going on, and the reason for that is because two things are affecting the tides. One is the sun and one is the moon. Everyone thinks the moon is the thing that's doing all the tidal influencing, but it actually turns out the sun is about equally responsible for the tides. So if we want to get in a little more detail even about tides, just because it's sort of interesting, it's not even so much about math, but I just think it's cool. Here's a little picture for you to look at. So this actually explains why we have the tides the way we do. The moon and the sun are both pulling on the tides, making a solar and a lunar tide. If they're both on the same side, then the two gravitational pulls add up and we get a really big tide. Interestingly enough, if the moon is on the opposite side, we still get the same effect where we get a very large tide. When the moon and the sun are at 90 degrees, we tend to not get as big a tides because they're not working together. So when we go and we look at a graph like this, this is actually showing here, we get a few tides in a day, so we can actually have a little look here. You'll notice, like, let's pick Monday. Around 2:15 a.m. we get a high tide, and then at 9:11, which is about 7 hours later, we get a low tide. Then at 3:20 p.m., which is about 6 hours later, we get a high, and then 8:06, which is about 5 hours later, we get a low. On average, though, the spacing between high and low tides is about 6 hours. So we wind up getting too high and too low in a 24-hour period. This should make some sense because as the Earth is rotating, the moon is going to pass by a certain point on the Earth 2 times in a day, and the sun is going to pass by sort of 2 times in a day. And I guess what I mean here is if you've got the sun, this is my terrible sun. Okay, there's my sun. Oh man, that's terrible. You get a large tide when the sun is on one side, or you get a large tide when the sun is on the opposite side. So I know the sun only passes by the same place once per day, but it is in line with this axis twice in the day. And same with the moon. The moon here is in line with that axis twice a day. So anyway, we wind up getting 4 tidal events per day because of 2 objects at 2 different positions per day. And they're spaced roughly 6 hours apart. Now, if you want to know why do the tides change in this sort of way here, where we see there's a general trending where the tides are getting higher and higher and higher, and the low tides are getting lower and lower and lower, this all has to do with the fact that in 28 days, the moon is making its full revolution around the Earth. So you'll actually notice in this here, we can see there's about a quarter of a period, roughly, and this is super rough, right? About a quarter of a period between like the average, and this would continue down low, and this would go up high. This is about a quarter of a period, and not surprisingly, we go from the 1st to about the 7th. This is about 7 days. So this fluctuation in the size of the high and low tides actually has a period of about 28 days, which is not really a surprise because the moon changes its position around the Earth in a slow revolution period of 28 days. So once we have a situation where the sun and the moon line up perfectly, we can get a very low tide and a very high tide. And then when the sun and the moon tend to be in different positions, we wind up getting sort of so-so tides without a lot of fluctuation. Anyway, there's just a little ramble about tides. If you're curious to learn more about tides, you should go look into it because they are actually quite interesting, and it's always shocking how few people understand some basic stuff like why the oceans go up and down. All right, so we're going to leave it there. This is your possible bonus question here. I won't give you the answer for this, but I'll leave it as something to think about. This would be a good question, hint, hint, wink, wink, if I was to ask you a question on, let's say, some sort of assessment for sine functions, for me to ask you something like this. And if you're looking for what the actual answers are, you can always go to Desmos. You can type this function up here into Desmos and figure out when the tidal height's 1.5. But I'll leave it there. And thanks for watching. Hope you learned something about the tides. Also math.